Everybody, what's up? Mr. Carafano here, outside in the garage for a little nighttime math lesson. So let's do it. Let's jump right in. So our focus today is to talk about how we can describe the shape of a dot plot, histogram, or stem plot, or how we can describe the shape of a distribution. It's a common phrase we'll hear. So lots of vocab coming up in this lesson today, so make sure you got your notebook ready, maybe some colors to do a little color coding, and let's get to it. So we can see the shape of a distribution using a dot plot, histogram, or stem plot. So when we keep saying this word distribution, right, as I just mentioned, when we say distribution, I mean, I don't really like what I'm about to do because I'm going to use the word distributed in my definition here, but we're talking about how the data is distributed across values as shown in a graph, right, a graphical display. Right, well, that's our histogram, stem plot, or dot plot. So we're going to see all sorts of vocab come up. And as you look at this list, right, maybe you can think about, right, maybe you have some ideas about what these definitions might mean. For instance, right, we might describe a graph as symmetric. I'm pretty confident we all have an idea what symmetry means. And so maybe in your head right now, you can picture a histogram or a dot plot that you would consider to be symmetric. We're going to talk about graphs as skewed left or skewed right. We're going to talk about graphs as uniform. We're going to talk about if something looks like the bell curve, right? Another thing, right? I think maybe we probably have all heard that phrase before, the bell curve, right? Maybe we can picture what a histogram dot plot might look like if we were going to have the shape of a bell curve. Some stuff not listed here. We're going to talk about the peaks in a graph, unimodal, bimodal, and we're going to just touch on some gaps in the idea of outliers in our data. So, right, just tons of vocab we're going to get through, and then the following days we'll start to practice and, you know, think a little more conceptually about why these shapes matter, what this information tells us, and so on. But for now, so symmetric distribution, like as I said earlier, right, I'm pretty sure we know what it means if something is symmetric. Sometimes I have trouble putting that into words, right? But we're familiar with an axis of symmetry, right? As we think about maybe the quadratic functions we learned about in Algebra 2, or even with an absolute value function or something. So right now, like, pause the video and try to either picture in your head or maybe jot down, draw an example of a histogram or a dot plot, right? You could draw a stem plot too, but right, easy to sketch a histogram or a dot plot that would look symmetric. Right, do that, like for real, do it, pause it, try to do that. So, right, here are three examples. Numbers are kind of irrelevant, right? Here are three examples of distributions that are symmetric. Right, so if something is symmetric, we're thinking, right, we can kind of draw a line down the middle and it's about the same on both sides, right? So any of these shapes we're looking at, any of these histograms here, I know this one looks like it's just a, this one in the middle here, this histogram, maybe looks like it's just like one big bin, but that's not the case, right? We just don't see the lines, right? So we're picturing this is a bunch of, this is like pretty sloppily drawn. Don't get too mad at me for my mouse skills here, right? But we're picturing a bunch of, right, different bins here. Nonetheless, right, all of these can be described as symmetric, right? Here I draw a line down the middle. This is about the same on the left and the right. Or if I folded like a piece of paper in half over this line, right, it would match on both sides. Right, same thing here. This distribution symmetric. This distribution symmetric. Right. So nothing crazy there, right? I think probably I could have skipped that slide, and many of us would have been comfortable identifying if a distribution were considered symmetric or not. Next up, talking about peaks. So we always want to pay attention to the number of peaks in a distribution. And the reason is, those are like kind of the modes, right? We're looking at the clusters in a data set. Where are the most common values, right? And so when we look at the peaks here, on this side, as we consider the shape, we want to think about the general outline of the shape, right? So like, I'm not going to trace along every single bin like this, right? Not going to do that. So we're thinking more of the general trend as we kind of follow along the outside of the histogram. Something like this. Something like this. So right here, right, in this graph on the left, right, there's kind of one peak, right? There's like one bump in the graph. We call that unimodal. Now, as we break that down, right, uni, of course, means one, right, like a unicycle or a, you know, other things with unit in it. But then we also see the word modal, right? And so that's referring to a mode. if we draw a histogram or a dot plot, whatever, right, all the same. Let's say I give a, I don't know, we ask for the number of, I don't know, math classes you're taking this year, right? If 1 is the most common, right? If that's the mode, that's going to create, that's going to become the highest bin. And so that mode is going to create a peak in this graph. It's kind of bothering me that I messed up this axis over here, but it's not going to mess up the idea of the shape, right? So if there's a mode, that's going to become the highest bin. And so then when we look at the outline of the shape, right, it's going to create that bump, right? So that's why we're using this word modal, right? In Una, 1 mode, right? 1 peak, 1 tall bin, 1 bump in the graph. I bet you can guess what this one's called. What do you think we call it if we have 2 high peaks in our graph? This, as I'm sure you would guess, we're going to call bimodal. A couple little side comments. So for something to be considered bimodal, this red example here, right, like kind of both of these peaks right above the 2 and above the 6 are exactly the same height, right? That's like a perfectly bimodal and symmetric distribution. So right there, I'm bringing up something else. We can describe these graphs in 2 ways, right? This graph is bimodal and symmetric. This graph over here is unimodal and symmetric. So I got a few tangents to touch on. Let me take a step back. So back to bimodal, right? Here we're seeing these are like perfectly the same height. That doesn't have to be the case. If I looked at a histogram and maybe 1 peak was up here and we had 1 bump like this where they weren't the same height, so it's not symmetric, we would still consider that to be a bimodal distribution. My other little tangent here on the side note, if we have a graph that looks like this, right, a graph that's unimodal and symmetric, that is our bell curve. So another piece of vocab that we should add that I don't have a slide for is the bell curve is any graph that's unimodal and roughly symmetric, right? Pretty symmetric. We're not going to be, you know, it doesn't have to be perfect, but it's got to be, you know, pretty close to symmetric. This bell curve, right, is a shape that's unimodal, pretty symmetric, roughly symmetric. That's also known as the normal model. So the normal model, the normal distribution is kind of the formal name of the bell curve. We probably hear bell curve more often, right? But those are all synonyms. So that's definitely something we want to add to our notes down here, right? In addition to what we talked about with symmetry and peaks. All right. So we've got this idea of symmetry. We've got this idea about peaks. But if something's unimodal, for instance, it doesn't have to just have 1 peak. That made no sense at all, but I'm not going to re-record the video. Hopefully you were like, dude, that's the opposite of what you said. What I meant to say was, if something's unimodal, that doesn't mean it has to be symmetric. For instance, we could have distributions that are skewed. So here, both of these distributions, both of these histograms have that 1 peak, right? Same thing here. The difference is where that peak is located, right? These are not symmetric. If I draw a line down the middle, right, these are not the same on the left and the right. So here we have data clustered on one side or another. So these are skewed distributions. Generally speaking, we're going to want to look at the tail of the distribution for the direction of the skew. So when we're trying to decide if we're going to call it skewed left or skewed right, we're thinking about where the tail of the distribution falls. So over here, this one, this is going to be a skewed left distribution, right? The tail is on the left side. Another name for a skewed left distribution, sometimes textbooks or whatever, I don't know, online sources, college professors, whatever. We might see this referred to as negatively skewed or skewed towards the negative values. And that's because, right, we kind of associate with, we picture a number line, right? We picture the negative values on the left side. I don't know why this is number line. Over here on this distribution, right, on the right, our tail, right, is on the right side. Most of our data is concentrated on the left, the lower end, with some high numbers creating this tail on the right side. And so this is a skewed right distribution, right? Tail is on the right side. And as you might guess, we can also refer to that as a positive skew. or skewed towards the positive values or something like that. So when we think about skewness, the reason we want to describe the shape, it's great to have a name for it, but if I tell you a distribution is skewed left, you can immediately kind of visualize and understand and have an idea about where the majority of the data is concentrated. Right here, if something's skewed left, bunch of data on the high end with a few low values to create the tail. Skewed right, most of our data is on the left side, right, and the lower numbers with a few high values to create that tail. So building off that idea, let's say I give a test, right? So I give a test in this class and I create a histogram or a dot plot of our test scores. Now it's important for you to know that I want us all to do well. So realistically, I would want the histogram to just be one bin or one string of dots over 100% because we all, whatever, paid attention, worked hard, and did our best, right? And that's great. So I want us to do well. But if everyone getting 100 is not an option, what do you think I would rather see in your test scores? Would I rather see our test scores distribute as skewed left? Would I rather see our test scores as skewed right? And why? So think about that. Remember, I want us to do well. So when we look at a skewed left distribution, right, that's what we're seeing over here. And I've already referenced this, but so skewed left distribution, right? Most of our data, so we can add this to our previous notes about that name, most of the data is kind of on the right or in the higher numbers with a few lower values. Now, what higher and lower mean, right? That's dependent upon the context, right? The number 4. If we're talking about GPAs, that's really high. If we're talking about a test score as a percentage, right? Not so much. 6, right? If we're talking about a test score, not great. If we're talking about your height, sure, 6 feet's pretty tall. That's pretty high. So high, low, right, varies with each context. So skewed left, right? Most of our data, the highest bins, the tallest frequencies are on the right side with a few lower values. Why wouldn't I use blue to match that? Whereas over here, if we have a distribution that is skewed right, the opposite is true, right? The majority of our data, most of our data is kind of on the left or in the lower numbers with few or some high values. Right? And that's what we see in this graph, right? Our highest frequencies, right? Our tallest bins in our histogram over on the left with shorter ones, right? Fewer high values. So hopefully you decided that I would rather see our test scores as skewed left, right? That suggests lots and lots of A's and B's and then a couple of, right, lower scores. I don't want anyone to get a low score, but we had to pick one of the two. Whereas if this were the case, if our test scores were skewed right, that would suggest most students are getting low scores like D's and F's, I guess, with a few high scores, right? If that happens, I got to look at myself and be like, all right, man, I got to do something different. Obviously, whatever I was doing as a teacher didn't work. Right, so just knowing that, right? If I know the test scores are skewed left without even looking at numbers, I'm feeling pretty good, right? Everyone got an A or B, we must have done a good job. Whereas if you just told me that the distribution of test scores was skewed right, I'm like, all right, now I'm a little bit nervous. I got to go back to the drawing board. One last thing about shape, right? So uniform. Think about a histogram that would look uniform. So first think about what the word uniform means, right? If things are uniform, what does that tell us about them? And so pause the video and try to sketch maybe a histogram that you think would be considered a uniform distribution. And hopefully you were thinking something like this, right? So uniform, we all wear a uniform at school. We all look kind of the same, right? We have all kind of the same clothes on, I guess I should say. So uniform, all the heights are about the same. So this graph in red, right, this is like perfectly uniform. Every single one of these bins is exactly the same height. Whereas over here, right, they're not exactly the same height. They're close. They're all roughly the same. So we might say this is roughly uniform. That was the worst little squiggly equal sign ever. So let me retry that, right? So that means roughly. That's a symbol for roughly if you're like me and you don't feel like writing all those letters or typing them. It's probably easy to type roughly than that symbol. But anyways, so uniform, all the bins are the same height-ish. And notice here, if something's uniform, right, it's also going to be pretty symmetric, right? This red distribution, perfectly symmetric. That's not a very good line. This gray distribution over here, pretty symmetric, right? Not exactly the same on the left and right, but pretty symmetric. As we tear through here, only a couple little more things, a couple of little things to touch on. So gaps. We always want to pay attention to gaps in our data. I'm now realizing that I had a histogram for this, and I did not paste it in apparently. But anyways, so if there's a gap in our data, we want to point that out. We want to say where there's a gap. Oh, there it is. So when you're describing that, you might just say, right, there's a gap from whatever, 40 to 60, right? And it's important to note that there's a gap because oftentimes that's some of the most important information we have about a context. So if I keep going with the test scores examples, like let's say this is from like 60 to 80 or something, right? So I note there's a gap from 60 to 80. Well, that's going to be really important to me as a teacher because that tells me that generally everyone got like A's and B's, 80 or above, or the rest people failed, right? With nothing in the middle, right? So like either I nailed it with people and they got the lesson, or people had no idea what I was talking about, right? And that's not great because there should be something going on in the middle. So that informs me about my practice. Or if I scroll down, I lied. I did have the histogram ready. I doubted myself. This is a histogram showing the sugar content by percentage for 49 different brands of cereal. And so here we can see it's not totally empty, but we can see there's generally a gap, right? There are not many cereals with 24 to 40% sugar, right? So that's how I might describe the gap, right? I might say not many cereals with 24 to 40% sugar. So as I think about cereal, right? Why do you think that's the case? If we look at this distribution, a few things you might think to yourself, right? Maybe pause the video and think, what shape is that distribution? How would you describe the shape of this histogram in yellow? And then maybe think about what accounts for that shape. And by that, I mean, why do we see these two chunks here, right? So hopefully you're thinking the shape is bimodal, right? We've got a bunch of cereals that have low sugar content, and then we have a bunch of cereals that have high sugar content, right? Bunch of stuff in the low end and on the high end. I'm just like really enjoying scribbling on that. And so, right, why is that the case? Why is there a gap in the middle? Picture the cereal aisle. Think about that. We can talk about it next time we see each other. But I really want you to think about it, so I'm not going to give it away. Why would a distribution of sugar content of cereals have this shape, have a gap with not much in the middle? Last thing we want to touch on is if there's an outlier, we always want to point that out. So an outlier is just an unusually high or low data value, right? Something surprising to us. Sometimes an outlier is just I typed 100 instead of 10 in the calculator or whatever in the software I'm using to make a graph, right? That's important. That's kind of a way to check. But oftentimes, there's something crazy going on with an outlier, something different, right? Something we want to investigate. So an outlier, an unusually high or low data value, right? A data value is kind of separated or like far apart from the others. That's not something we want to ignore. That can sometimes be the most informative part of our data. Like maybe this is, I don't know, hours spent on a project I gave people and everyone took at least 5 hours except for this one person. Like, what's up with that? How come it only took them 2 hours and it took everyone else so much longer? Maybe something sketchy is going on. I don't know. But the point is that this outlier is something I want to investigate. Or maybe I'm just curious, right? I see the ages of the best actress Oscar winners, I think. And I'm like, oh, all right, so it's pretty unusual for an older actress to win. I wonder what was going on there. I wonder what movies those were. So we always want to look deeper into the outliers. And so you might just say, when you're describing the shape, you might say it's unimodal and symmetric or something, but it looks like there might be one outlier or something like that. So no fancy vocab for the gaps or the outliers. You're kind of, other than outlier, you're kind of just telling me where the gap is or where the outlier is. We'll get more into outliers with box plots. So that's really it. So to kind of recap, we got to be able to determine if a graph is symmetric or if it's skewed left or right. We have to be able to determine if a graph is uniform, right, no peaks, or if it's unimodal, 1 peak, or if it's bimodal, 2 peaks. And if you're curious if there are more than 2 peaks, we could call that multimodal. We want to be able to identify gaps in a data set, and I'm going to say by number, right? So we don't want to just say there's a gap in the middle. I've said that a couple times, but we'd rather say there's a gap from 24 to 40% in the sugar contents. And then we want to identify possible outliers. There's a possible high outlier, possible low outlier, and maybe low outlier, and maybe how many there are. So we'll see all these things come up in practice as we continue to create graphs and now add this element of describing their shape. That's it. You'll see that come up in your practice, but if you want to look at it right now, go for it. And I think we're done. So let me stop sharing so I can make this goodbye less awkward, and I'll see you guys in class.